Welcome back, Calculus Advanced. We're going to start, I believe it's 4.7 in the book, Optimization, Day 1. I'm probably going to give you a note packet that has Day 1 through 3 on it. And this is the last section in Chapter 4 before we go ahead and have a test. These optimization type of questions are going to remind me, or might remind you of a little bit of a related rates questions, only because they're like applied calculus questions. But the idea of optimization, you're trying to find like when someone says like find like the optimal route, like what's the best route, what's the most efficient route. Um, we're trying to find the dimensions of values that will maximize or minimize a certain value. So if you want to find like the optimal route, maybe it's like the quickest route, or you're minimizing time, or you're maybe maximizing production in a certain amount of time. So just trying to find max and mins of situations. We've been doing this for a while, and now we're just doing it with applied questions. So, a quick example to start us off. Two positive numbers, x and y, have a sum of 40. Determine the values of x and y that will have the greatest product. So, two numbers that add up to 40, but they multiply to be a big number. You can almost think of it as like two numbers have to add up to 40, but the area of the x by y square has to be as big as the biggest possible area. So like you can think like, well, 1 and 39 add up to 40, and they multiply to 39. 2 and 38 add up to 40, and they multiply to 76. I think 20 and 20 is going to be the answer. They add up to 40, and that's going to be 400. But here's how we can get something like this without maybe having to guess and check. So here's the idea. All right. We're trying to maximize the product of x and y. If I want to write an equation for that value, I'm going to call P that value. The product of x and y is just x times y. To find the max or min, we set the derivative equal to 0. So that's how we find our max and mins, or DNE. Right? In other words, we find the critical numbers. Find the crits. So the issue here is that P is a two-variable equation, so we're going to need a secondary equation. So that I can write P in terms of just x or just y. And we have that secondary equation right here. This is also known as the constraint. So secondary equation or constraint. So that word is constraint, that word is secondary. And the constraint is that the two numbers x and y have to have a sum of 40. So this is kind of like locked in. You can't just pick any two numbers, but they have to add up to 40. Which is fine. We can make that happen, and that's going to help us a lot actually. If I know x plus y is 40, that's equivalent to saying y is equal to 40 minus x. Just subtract x on both sides to isolate the y. So now my product equation, which is x times y, is really just x times 40 minus x. So I had a long discussion with Mr. Dobo and one of the Smathers twins, and we agreed that purple is a primary equation color and yellow is a good secondary equation color. So the primary equation is what I'm trying to max or minimize. I'm trying to maximize the product. So to do it, we're going to find the derivative that equals 0. Before I do the derivative, so I can avoid a product rule here, I'm just going to distribute. So that's 40x minus x squared. The derivative is green, obviously, so the derivative is going to be 40 minus 2x. This thing is going to exist everywhere, so I just need to find out where it's 0 to find the crits. So let's see, add 2x to both sides. I get 40 equals 2x. Divide both sides by 2. I get 20 equals x, which is what we expected, right? If x equals 20, plug it in to find out what y is. So y is just 40 minus x, which is 20. So these are my two numbers that add up to 20 and have the greatest product. So that's my answer. Did it ask for what are x and y? Determine the values of x and y. If it asked what the product is, we would just multiply them together. We skipped one step, but we didn't really need it, I guess. So the derivative was 0 at 20. Normally we plug in a number less than 20 and greater than 20. So if I plug a number that's like less than 20 into this derivative, a number less than 20 times 2 is going to be less than 40, so 40 minus that is going to be positive. If I plug a number bigger than 20, 2 times that number is going to be bigger than 40, so 40 minus the number bigger than 40 is going to be negative, which makes sense. We thought we'd have a max here because we're trying to max out the product, and this sign chart checks out that we do have a max, not a min. Most of the time, I'm not going to bother checking these unless I'm not sure, because if there's only one answer, it's probably the one we're looking for. The intuition should carry us through. So take a minute to pause the video and copy down these steps. These are general steps for optimizing. So step 1, identify what you're trying to max or minimize. That's going to be our primary equation. Determine what variables and parameters are involved. Making a diagram is going to be helpful. So write a primary equation for our max and min values. Then we're going to need our constraint equation or our secondary equation to rewrite your primary equation in terms of a single variable. And then use calculus to find the max or min. In other words, take the derivative set it equal to 0 and do all that fun stuff we've been doing. So here's an example. Copy, or I don't think you have to copy it down because it's written for you. Queen Jasmine from Agrabah is designing her castle, which will be a rectangle built up against a cliff on one side, so no wall on that side. She has enough stone to make 12 kilometers of wall. What should the dimensions be of the castle to maximize the area enclosed by the walls? So we have kind of a bird's eye view. So looking down, we have 3 walls and a cliff that we don't need to use to make a wall because the cliff is going to kind of be that wall. So I'm just going to call these dimensions, I don't know, x and y. So this is also going to be x because it's a rectangular castle. So what am I trying to max or minimize? I'm trying to maximize the area. So my primary equation, which is purple, is the equation I'm trying to maximize, which is the area. And the area of a rectangle is length times width, which is going to be y times x or x times y. So again, taking the derivative, just like before, in terms of 2 variables, so I need a secondary equation or the constraints here so that I can write my primary equation in 1 variable. So what am I constrained by in this problem? We're building a nice wall for the castle up against a cliff. There's enough stone to make 12 kilometers of wall, so we only have enough to make 12 kilometers of wall. So that means the perimeter, if I take x, y, and x and add them together, we only have enough to make 12 kilometers of wall. Which means, let's see, that's the same thing as saying 2x plus y equals 12. And if I want to solve this for y, subtract 2x on both sides, and we get that. So there's my primary equation. What I'm going to do is replace y with 12 minus 2x. So now I can write my primary equation in terms of a single, in parentheses, useful variable. Okay, so we're left with 12 minus 2x. And now just calculus. Well, I guess algebra. I'm going to first simplify this. So that's going to be the same thing as 12x minus 2x squared. So we can avoid the product rule. Now I take the derivative, which is a green color. 12 minus 4x. We set this equal to 0. It does not exist. We don't have to worry about it does not exist because it exists everywhere. Add 4x to both sides. Divide both sides by 4. So x equals 3 kilometers. So this is going to be 3 kilometers. This is going to be 3 kilometers. We got to find out what y is, which is easy enough. Y is going to be 12 minus 2 times 3, which is 12 minus 6, which is 6. So this is 6 kilometers. So she has enough to, what should the dimensions be of the castle? So the castle should be, 3 by 6. And that's it. If I want to find out what the area would be, it's going to be 3 times 6 is 18, which it's not asking us to find it. Oh, wait. We want to maximize the area. Yeah, so the dimension should be 3 by 6, and the area is 18, but it just asks for the dimensions. All right. And looks like we got one more. All right. So here we have a manufacturer who wants to design an open top box with a square base and a surface area of 108 square inches. What are the dimensions to maximize the volume? So I want to find out what am I trying to max or minimize. In this case, it's volume. So that's going to be my primary equation. And it's for an open top box with a square base. So I want to find the volume of an open top box with a square base. I think it'll be helpful to draw this. So the base is going to be a square. So I'm going to call the base x by x, so it's equal. And I don't know what the height is. It looks to be about the same, but I'm just going to call it y. So my volume is going to be, the volume of it is the area of the base, so it's x times y, which is just x squared y. You could use L and W and call it like L squared W if you want. I'm just using x and y because I feel like it. So I have my primary equation, but it's got two variables, so I need a secondary equation. What's my constraint here? Well, let's see. The surface area is 108 square inches. So that's my secondary equation. That's my constraint. The surface area, I'm going to call it SA instead of A, but you can call it A. I don't care. The surface area of this whole thing, and remember, it's an open top box. So we just need to find the area of the four walls and the floor. So let's see here. So the area of the floor is x by x, or x squared. The area of one wall is x times y. And there's four walls that are all x by y. The front, the back, or excuse me, the left, the right, the front, and the back. So there's four walls that are x by y. Now there is no roof, there is no top, so I don't need to worry about the top. So that's going to be the surface area. And we know that's equal to 108. So I certainly don't feel like solving this for x because x is a quadratic. So we're going to solve this one for y. So subtract x squared on both sides. So 4xy equals 108 minus x squared. Divide both sides by 4xy. Excuse me, just by 4x. And now we've isolated y. This is my primary equation still. I'm not going to bother simplifying this. I'm just going to leave it as is. And so this y needs to get replaced by this. This y. Okay, so back to my primary equation. I want to write it in terms of a single useful variable. So it's going to be x squared times y. And I'm going to replace y with this expression here that represents y, which is 108 minus x squared over 4x. Again, to avoid the product rule, let's do some simplifying here. And again, this is just algebra. This x on the bottom is going to divide out with one of those x's on the top. So I can just distribute that 1x up top. So x times 108 is 108x. And x times x squared is x cubed. So now, again, back to the calculus, we got to find out the max or min of this. So we're going to take the derivative, set it equals 0. So the derivative is going to be 108 minus 3x squared. X squared, quadratic is defined everywhere, so we're just going to worry about when it's 0. Add 3x squared to both sides, you get 108 equals 3x squared. Divide by 3. Ooh. Sorry. I forgot this is all over 4. In this one, I will actually rewrite again. Sorry. Oopsies. Okay. So if I divide 108 by 4, this is going to make this problem a little bit easier. That's going to be 27x, and then this is going to be 1/4 x cubed. So I just divided both pieces by 4 so I can have a nice, two-term polynomial here. So now when I take the derivative, that's just going to be 27 minus 3/4 x squared. Again, set it equal to 0. That means 27 equals 3/4 x squared. Now, to undo multiplying by 3/4, I'm going to multiply both sides by 4/3. Turn red. Come on. There we go. So the 4's cancel, the 3's cancel. 27 divided by 3 is 9. 9 times 4 is 36. So x equals plus or minus 6, but really 6 because we can't have a negative side length here. Okay, so what dimensions should we have to maximize volume of the box? Well, the base has to be a 6 by 6 square, and the height is going to be whatever 108 minus 6 squared, which is 36. 4 times 6 is 24. Which comes out to 3. So that's what the dimensions are of the box, and I kind of wanted to check it just so we can be in agreement here. 108 minus 36. Sorry, guys. $72, and then 72 divided by 3 is 24. Okay, so we're good. Anyways, so we'll get some practicing in class. There's gonna be a couple more days of this. Again, feel free to like, comment, and subscribe. Ring the bell for notifications. And if you liked it, just go ahead and smash that like button for me. This video again was brought to you by Raid Shadow Legends. Play today.